Okay, hello and good morning. Today in this video, what I would like to do is I would like to define a contour integral crack with the crack face interface. Now that is very important and interesting for thermomechanical fatigue crack case, because generally what is happening in our model and simulations is that when there are compressive stresses in the model, the crack faces overlap and we do not get an appropriate energy release rate at the crack tip due to this anomaly. So I already made a small video before with an XFEM crack. I believe it was not so good. It was not the best one basically. So today I will start with a contour integral crack definition. Will apply compressive stresses and show you what the problem is, and then basically the video is about teaching you how to define the interface between contour integral crack faces, or in the future XFEM crack faces, which is very helpful when there are compressive stresses in the model. So let's start. We already have a block apart, we already have a material model which is thermomechanical model, but here in this simulation we will only use the mechanical part. Step is already defined, it is temperature coupled temperature displacement step, but we will only be using the mechanical part of this, not the temperature part of this in this simulation. I have already requested appropriate thermal and mechanical responses. Now this is what I want to play with. I want to delete the predefined field, or we can keep it, but I want to delete the applied heat input, so it is not calculating this. And then we have basically applied roller condition in X direction on this side, and we have applied a compressive displacement on this side, and I want to define a crack here, a long big crack, just to have a clear distinction. Let's see, it has been quite a while since I have defined cracks, and it's not something I'm very good with. Let's say I want to create partition on the face, sketch. Okay, what it says is can only assign mesh attributes here. So okay, so let's make it independent then. Make independent. So now we want to sketch on it, and it says the mesh will be deleted. I'm completely fine with it. Defining contour integral crack is tricky here, so I will just follow up the SOPs which I know work. So this is a crack, and to define a spider mesh on its tip, what we do is, oh, this is quite big. What we do is we define a small circle, and then we define a big circle around it. Let's clean up the dimensions. It has a dimension of 0.003, and the bigger circle should be 5 to 6 times larger than that. So yeah, seems good to me. Okay, then I would also like to section it from this end to this end, so we can apply a homogeneous mesh here, and rest seems okay to me. What I would like to do other than that is to clean up the mesh around the crack. What I would like to do is do this. This sectioning is just to clean up the mesh in these areas of the brick, and yeah, so we can get a good structured mesh. Seems okay to me. So in the end, you will have this part where we will define triangular mesh, and this part where we will define a structured mesh, so it is easier to calculate the energy release on the crack tip for the numerical simulation. And this is the part where basically there will be a rough mesh, and then this is the part where it will have a structured mesh. Let's define the crack. So we go into the engineering features. Crack is contour integral. We only have one crack, so it is this crack. Select the crack front. This is the crack front. Q vectors, we want to define the crack propagation in the direction of Q vector, so select this point, any other point in the direction of crack propagation. Singularity, it is 0.24. I don't know why, but this value works. Now this has collapsed element sites, and we want to duplicate nodes. Rest everything is fine, seems okay to me. So we have defined the crack. Now we want to define the crack seam, so we go into special crack, assign seam, and we select this by pressing down the shift button and selecting this. Now this is the crack seam, so basically the crack, and this is the crack tip. Done. We see that it has highlighted it, and we press done. So the crack has been defined in the block, and what I want to do next is I want to mesh it, and now that is the tricky part. Initially, let's do the easy thing first. I want to control the mesh controls here, and that is structured. Now this should also be structured. This can be free, and this has to be free. I don't know. Okay, we'll see. Now this should have only one element. They should have, let's say, 7 elements. Both, I don't want them to change, so do not allow them to move. Okay, then I want this half, this half, this half, and this half to have a specific number of elements. Let's say 20. I want to see if it is good enough. Seems okay to me. We can increase a bit, 25. Okay, so distance between these points and distance between these points is more or less same. I'm happy with it. This element will be quite large, so what we do here is we apply mesh biasing. So I don't know from where. Yeah, so single bias. I want to flip this bias to the other direction, and I want to see. So now you see that there is a big difference here, and it is getting closer here. Number of elements we can increase to 12. So let's see, it becomes something like this. Seems good to me, because here then we have almost same distance, bias ratio 6. I used to have a chart which seemed to be work fine all the time, but yeah, for now I think this is okay, and rest of the block can be meshed as is. I want to choose coupled temperature displacement simulation model. It will take some time to solve. Let's select plane strain model and mesh it. Now you can see that we get a really nice spider mesh on the crack tip with wedges pointing at the crack tip and rest of the contours around the crack, really nice structure. And then there is due to this mesh there is a little randomness here, but the rest of the block is very nicely meshed. So yeah, this is something which we are targeting, and a homogeneous mesh on both sides of the crack. So yeah, we have defined our contour integral crack. Next up, what we want to do is we want to apply boundary conditions. I had applied quite a hefty boundary condition. I would change it now. I had applied a boundary condition of 7mm displacement. I will change it to 3.5 centimeters. So we are compressing it in this direction, and we have a roller condition here, and we have fixed it from here. I'm applying compression because we specifically want to see how the crack behaves under compression. Then I will show you how it behaves under tension, which is good enough already. And what we want to do is then I would show you how to define the crack face interface, so the problem, or we rule out the tension part and just focus on the compression here. Okay, so when I am creating this, I cannot create this interface. Parallelization to CPUs, okay, and submit. Oh, it says that no history outputs. Okay, I can associate a history output with that, no problem. Crack. Okay, in this, not with this, but with crack. So number of contours are let's say make it 5. I want to see J integral, and yeah, submit. Monitor. Ooh, degree of freedom 11, at least 1, or degree of freedom 1 through 6 must be active with the model for coupled temperature displacement. Okay, that's an issue. That's an issue because what I did was I chose mesh type plane strain, but basically the error is because I have to select this coupled temperature displacement. Let's select reduced integration type, done, and remesh it. The idea is to just make the simulation run faster so we can quickly look at the results. I would also like to increase this to 0.5, so just to make the simulation a bit faster, because yeah, we are not really collecting results but just getting an idea of why and how things are happening and what we need to do to get this done. Let's look at the processing. Okay, simulation seems to be running quite fast. Yes. Okay, while it is running, let's look at the results. So you can already see that the crack opened up, but due to the applied compressive loads, the faces are overlapping. You can already see that happening. What I always do is I always see the common, so it is showing it is already showing the scale factor of 1, so realistic deformation. If I see this, so basically this is what's happening. The crack faces are overlapping. What happens is that during simulation the crack faces separate up, so there is a separate node to that side and separate node to this side, and then due to the applied load, because there is no interface defined between them, so they are overlapping, and due to this overlapping we can get wrong results on the crack tip during compression. Normally the cracks initiate and propagate under tensile load. Under compressive load they generally are initiating and propagating in ceramics, but usually is not the case in the case of metals. But in thermomechanical fatigue case, because there is because there is heating and cooling, there is a compression cycle, and after that there is a tension cycle, and in each compression cycle basically the crack closes up, and in the tension cycle it opens up again to absorb energy, and that is a complicated problem. So therefore we need to understand or to define the crack face interface, so this kind of problem does not happen when we define that simulation which we are targeting in the future. You already see the problem. Let's keep it running, and what I want to do is I want to copy this model, name it v2, and modify the changes and show you how this works. Okay, so we have this model, assembly is this one, and what we want to do is we want to define an interface. Initially what we need to do is we need to define interaction properties. Now a lot of researchers have already done research on what is the friction coefficient between the crack faces during compression under thermomechanical fatigue load case, and it depends on multiple factors, and there is a lot of data already available on Google Scholar and by many other researchers. I'm not going into the detail there. What I will just do here is I will define a contact, a frictionless contact, and that is something which you can then later modify if you want. I will show you how. Frictionless. Okay, and I want to define a mechanical, normal, and geometric behavior. So we have defined a frictionless contact. If you want to define a specific friction coefficient in the crack face interface, then you can select penalty and define a friction coefficient here. And yeah, so let's say 0.3 or 4 or 1, and that is how you define the friction coefficient. For now we are not interested in that, we have just defined this. And now what we want to do is we want to define interaction between these two crack faces. What I would like to do for that is I would like to go into the assembly, and I would like to define the surfaces, and I would like to define surface of, for example, I would name it crack top using mesh, and I would continue. Now what I would like to do is I want to select the upper side of the mesh here. So an idea of doing is to remove mesh. Okay, so not this faces, really, surface, remove, yeah, so here elements, and remove these elements, and remove these elements. Oh my god, and remove these elements. Do not remove the last element, because then this point is common between both elements and it creates a problem for ABAQUS, but we can remove these elements. Now this is the face what we want to define as a crack top. Select the regions for the surface. I will select this region. Nicely selected. Okay, and now we have defined crack top. Now I want to define in the mesh crack bottom, and quickly I can use just this command which reverses the selection, and I select this. Done. And now this is also selected. What I can do is I can see the whole surface. And now, interestingly, to define the interaction between these two, what I do is I go to this and I select the initial and surface to surface contact. This is what I want to define, and I want to name it crack interface. Select the master surface. That's it, crack top. Select the slave surface, crack bottom, and the surface interaction has been defined. Now we can see that the interaction between these two surfaces is defined. This is how we model it, and I want to run the simulation again. V2 crack int, and basically this is the simulation model with interface defined between the crack faces, and the other one was without it. And let's talk about it after the simulations are complete and post-process it quickly. Okay, so it was taking quite long to solve this problem, as there is an issue here with the mesh and the crack tip. Probably due to mathematical instabilities, the simulation convergence takes time and is not solving quickly. So this is also a problem. You can see that when there is no crack interface defined, it was taking, I think, more than 15 minutes. But on the other hand, when the crack interface was defined in version 2 of the simulation, you can see that there is no overlap here. There is an overlap here in these nodes because we did not define the crack face interface, and this is a problem with contour integral crack, that we unfortunately just cannot define a crack interface here on this element. But this is a very small problem as compared to the rest of the case, and it does not really affect when we are applying thermomechanical loads, because this overlap is really super small and does not really affect the results. And we see that we obtain similar results under compression, that there is compression in this direction, and we can see that the whole bulk is deformed, and probably there will not be any much stresses, but rather strains when we will look at it, because the material is able to deform in this direction. So this is how we, now you see, this is how we define interface between these two crack faces. And in the future I want to make a simulation where I want to apply a cyclic load or cyclic displacement here, and you can see that the crack faces open up when a tensile load is defined, and the crack faces close together and basically join together to form a contact when there is compressive cycle. And this is interesting case, an interesting thing to learn and apply in our simulations when there is a crack and the model is going under compressive loads or compressive stresses, because then this can basically give a better approximation of results. So yeah, and if you want to check out how to post-process the results for these cracks, do check a previous video which I uploaded. I'm not doing it here, and there I did it with quite much detail, like how to post-process the crack propagation results, or contour integral crack results. And there I had also applied compressive stresses in this domain, and it was quite interesting to see. So yeah, see you in the next video, and thank you and bye.